little bit and look at these packing patterns, or stacking patterns is what I meant to say. Stacking pattern, and the unit cell that manifests as a result. Okay, so this is our simplest way to pack atoms together. And it's also the least efficient way to stack the atoms together. So this is our cubic packed crystal structure. And this is now where the layers of atoms are going to be A. And what makes this an AAA layer is, notice now we're not squeezing those atoms in between one of the holes, right? If I look at this above, let's just draw 6 of these things. Right, so my holes are right there. If I started stacking atoms on the holes, that would make it a B layer. Instead, what's done is, I'll just change color here to demonstrate. Sure, let's get this color. So now to make this, we're just stacking the atoms right on top of each other. And so that's going to make it an A layer. And hopefully what you can also see now, why we call this a cubic packed, because it makes a nice little cube there, right? If I were to draw from the center of each atom a line, then I would get this nice, perfect little cube. Okay, so we call this unit cell the simple cubic unit cell. Sometimes we'll see it abbreviated as SC. I want you to be familiar with this arrangement. So there are particles located at 8 corners of the cube in the unit cell. So then, of course, if we were packing another unit cell in there, we can see that each unit cell shares atoms with a neighboring unit cell, and so on and so on. So that's what makes this a repeating unit. Okay. So moving on. So now if we look at our next simplest, our slightly more complicated, now we got our square closest packing. And here, remember, our closest packing model is going to be more efficient. This is, hopefully you can see that, where now we're going to stack the successive layer of atoms on the holes. So now, right, I would stack a layer here and here and here. And then, of course, I would have another pattern ready to go there, right? And if we were to zoom in and find the simplest repeating unit of that, okay, this kind of looks like the simple cubic in that we have a cube that we're making from the corners, but now we end up with a full atom in the center of that unit cell. And so that's why creatively we call it a body-centered cubic unit cell, because there is a full atom in the center of that unit cell. Okay, and then of course we also have other atoms located on all 8 corners. Okay, so let's look now at the cubic closest packing. So remember, this was our square closest packing. This is our cubic closest packing. And this is given by an ABC, ABC. This one can be a lot more difficult to visualize. So often that's done by starting with one atom. Now we have this B layer, which is going to go right there in the hole of the next atom. And now by rotating another layer 180 degrees and dropping it down into those sweet spots into the next series of holes, that will create a C layer. So we have A, B, C, and then we can start repeating the process again by sandwiching an atom right there in the middle. This also becomes very difficult to visualize what the unit cell looks like. So if you're not able to see it, I don't blame you at all. It's difficult for me to see this one as well. But the way that this ends up working out, when we draw the unit cell from this, you can see that we end up, for one, with atoms on each of the 8 corners, right? So we have atoms on each 8 corner. And now, if we look at the way that this is named, face-centered cubic, what we end up now with is 6 atoms on each of the 6 faces. So if I were to draw just one of the faces like this in this two-dimensional array, we recognize we've got atoms on each of the corners, okay? But now we have an atom on each face. So for example, on this face right here, I have an atom sticking out like that, so it's in the same plane as this. I have another atom in this plane, of course, another one in this plane, another one in this plane, and now we have to imagine this is three-dimensional, right? So there's a face coming out at you, and there's a face going behind the board, and there's an atom in each one of those faces, okay? Hopefully you can visualize that. So for example, I see 1, 2, 3, 4, 5, 6 atoms all on the 6 sides of our cube. And the final one that I'll describe that I want you to be familiar with is the hexagonal closest packed crystal structure. So this is a closest packed structure, so that means the atoms are going to fit down into the holes. This becomes another one that's once again very difficult to visualize. But as you look at this thing, hopefully you can see that's making a hexagon. And we can actually make a unit cell out of this thing by drawing a rhombus. So that's a hexagonal unit cell. Oh, I wrote SC right there, but we'll just call it, I don't have an abbreviation for it, sorry. Hexagonal unit cell, close packing arrangement, particles located at 8 corners of the cubic unit cell. So again, this one is really hard to visualize, and we're not going to do a whole lot with the hexagonal unit cell. I mostly want you to be familiar with the face-centered cubic, the body-centered cubic, and the simple cubic. Those are the unit cells I want you to be intimately familiar with, and just be aware that this hexagonal unit cell exists. Okay, so let's summarize all of that. So if we look at the lattice name, so I'll just combine lattice name and unit cell. So simple cubic, okay. The type of packing is cubic. The stacking pattern is A. So this becomes more difficult to work out, but we're going to start seeing this momentarily. The number of nearest neighbors in each atom in a simple cubic is actually going to be 6. And again, we're going to start seeing that manifest soon. And we're also going to learn how to calculate this packing efficiency soon. For now, I'm just going to give you the number. So it turns out to be 52% for the simple cubic. So what that means is in a simple cubic unit cell, 52% of the space is atoms, 48% of the space is empty, which is incredible to think about. This is a solid, but 48% of its space is nothing. So next one I want you to be familiar with is the BCC, the body-centered cubic. Okay, so that has that's the closest square closest packing. Okay, so I'm just going to call it closest. So we recognize that the atoms are fitting down into those little holes. That makes the AB pattern. There ends up being 8 nearest neighbors, and the packing efficiency jumps up to 68%. So that's significant. And last unit cell we'll talk about is the FCC, the face-centered cubic. We know that's also a closest packing model. This one adopts the ABC pattern. As it turns out, there's 12 nearest neighbors, and this brings the packing efficiency up to 74%. So what we're going to see, these numbers and these details really matter for these solids. They are what's dictating the physical properties of those atoms and molecules and ions. And we'll talk about that in the next video.